Welcome everyone to our post-launch session. This will be the third session about proof systems. And our first speaker is Bini Chen, who will speak of Lattice Fold Plus, memory efficient proving at scale.
Thanks for the introduction. Hello everyone, my name is Bini. Today I'll talk about Lattice Fold Plus, which is a folding scheme based on lattices that enable more memory efficient and scalable proof systems. This is joint work with Dan Bonnet from Stanford University. So we all know CK-SNARK is a really powerful primitive that allows one party to convince another party that certain expensive computation was done correctly. And recently, we have seen many new advanced applications for SNARKs, such as proof of learning and so on. All these new applications have a common paradigm to let the prover to generate proof for some really, really large statements, whose circuits can be as large as billions or even tens of billions of gates. So what we want is a new system that supports more scalable prover for proving large statements, and if possible, also post-quantum security for systems. Recently, there's a very popular framework, which I call piecemeal SNARK, to combine the so-called accumulation scheme or folding scheme with SNARK together to obtain a scalable and memory-efficient proof system. The high-level idea is to split, fold, and prove. So what does it mean? Given a really large computation statements, we try to split it into many smaller statements, and the goal is to prove the correctness of these many small statements. And then with the help of so-called folding scheme or accumulation scheme, we can reduce the checking of these many statements into the checking of a single root statement on the root of this tree. Notably, every node in this tree is just a statement that's not much larger than a single chunk statement here, plus some extra logic about the folding verification. So the root statement is actually pretty small, and we can afford to run a SNARK to obtain a succinct proof in a very efficient way. On the other hand, for the folding scheme, it is a weaker primitive that allows for much, much faster and more efficient constructions. So even if it needs to handle really large amount of information, it can be pretty fast. For example, the state-of-the-art elliptic curve-based folding scheme like NOVA, it can be more than 100 times faster than a SNARK in the elliptic curve setting. However, elliptic curve operations are quite expensive compared to those hash-based proof systems or lattice-based proof systems. And our focus today is to obtain a public coin interactive folding scheme in the lattice setting that replaces these Peterson hashes with ring-based added commitments that can be much faster. And we focus on this public coin interactive setting. If you want a non-interactive scheme, you would have to use this Fisher-Shamir transform to make it non-interactive. So what exactly is a folding scheme? It's a public coin protocol between a prover and a verifier for checking two statements are true. The first statement is in this relation that should be NP complete so that it can capture arbitrary computation. The other relation is called accumulated relation that can differ scheme by scheme. The goal here is that after execution of this protocol, if the verifier accepts, then it will convert the two input instances into a new instance, and the prover will derive a new witness for these new statements given the input witnesses. So essentially, we have reduced checking of two statements into one. It needs to satisfy some similar notion of completeness, soundness, and succinctness as in SNARK. For example, complete means if the input statements are true, then after execution, the output statement will also be true. And soundness saying that if any of the input statements is false, then with high probability, either the verifier will directly reject or the prover cannot provide a valid witness later for the output relation. And succinctness means that the verifier complexity here should be sublinear in the size of the input witnesses here. And also the communications should also be sublinear. But we note that this is actually a weaker primitive than SNARKs. Why? Because this accumulated relation can be quite expensive to check, and its output statement is not necessarily to be succinct. So it does not imply SNARK, though SNARK implies a folding scheme. But the advantage here is that we can have much more efficient construction for these new primitives, which is already sufficient for our applications. As I said before, my focus here is the lattice-based schemes because it is plausibly post-quantum secure, and even more importantly, compared to those Peterson hash-based elliptic curve-based folding scheme, it leads to even faster prover because we can replace with this ring-based anti-hash function that's even faster. And notably, compared to lattice-based succinct arguments, we can obtain a much more succinct verifier in a much easier way because we are dealing with a weaker primitive that's easier to construct. Before our work, there are several elegant schemes from lattices to build folding scheme. It starts from this work called latticefold, which builds a folding scheme based on this module SIS assumption and ring-based anti-commitments. And also there are some variants of it that improve it in different perspectives. However, all these schemes suffer one drawback in the sense that the prover needs to do more work than just committing to the input witness. And this makes the end-to-end system actually slightly slower than elliptic curve-based folding schemes, even though we have much faster hash functions and the commitment schemes. The reason that the prover needs to perform more computation for computing more helper commitments during the folding scheme, which is not the case in the elliptic curve setting. So the question is, can we address this limitation and make lattice-based folding even faster than elliptic curve-based foldings? So for that, we introduced latticefold plus, which is a new scheme that's still based on the module SIS assumptions, but leads to much faster prover and efficient succinct verifier compared to previous works. And the key observation here is that you make use of this quotient ring RQ, which is this residual ring with respect to these cyclotomical rings of dimension D with respect to some prime modulus Q. And here the kappa D, let kappa T be the rank of the module SS matrix. The corresponding prover in amortized wise, it only needs to perform about kappa log D small field multiplication plus kappa D field additions for committing and proving every ZQ witness elements in the MP witness. This is significantly faster than Peterson-based schemes, and it's also highly parallelizable and hardware friendly. The verifier is also pretty succinct. It's dominated by this kappa D number of small 2-to-1 small field hashes in terms of circuit complexity. So the key enabler for these improvements is a new range proof that removes some kind of drawback of the previous latticefold, which I will explain more in detail later. But in sum, it eliminates, decrease the number of helper commitments to be computed by prover by a factor of log D, which is quite large and leads to much more efficient prover and verifiers. So let me give a quick technical overview now. So typically we need the folding for MP complete relations, but now let's consider a slightly simpler problem to just prove the commitment opening relation. And as I said before, we replace these Peterson hashes with this lattice-based, ring-based attack hash functions, which is more efficient. So this relation is saying that given the witness, it is in the relation with respect to an instance, if it is an opening of these ring-based attack hash functions, so Cm equals AF. But moreover, it has to satisfy its norm bound that the infinite norm of this ring vector is no more than B. And this is necessary for the binding property for ITAC commitments to reduce it to the SIS or module SIS assumption. And our goal is to obtain a folding scheme for these statements about the commitment opening relation. And in the elliptic curve setting, this is actually really simple to do. Well, what you do is just do a random unique combination for this commitment opening relation. The verifier sample a random scalar, the prover randomly combine this witness vector together, and the verifier randomly combine the corresponding Peterson hashes using this scalar. And given the linear homomorphism of Peterson hashes, this works really well. However, in the lattice setting, this is much more complicated because we have this extra constraints on the norm of the witness. So that means the output witness have to be no norm, even if you do the random combination from the inputs. To address this norm blow-up issue, in the literature, there are two main techniques. The first is to use those no-norm challenges in the set of R. So let S to be the set of polynomial in this ring R, for which every coefficient is in the range of 0, 1, and -1. Then now what you do is you sample elements, challenge elements from this set S and do the random combination over this ring R. There are 2 points. First, this challenge set now can be exponentially large, so that leads to a really small negligible soundness error. On the other hand, because every coefficient of the elements is really small, the resulting folded witness is not much larger than before. However, it still has some kind of norm blow-up, which is linear to the degree of the polynomial. It turns out this is actually not sufficient in the folding setting, because we really want to fold for many steps. We want to make sure after many folding steps, the resulting witness are still no norm. So ideally, what we really want is to have a scheme that has no norm blow-up at all. And to do that, we need another technique called decomposition, which is already widely used in the homomorphic encryption world. So the idea is the following. Given a long vector of ring elements, we run some deterministic algorithm and split it into k different vectors of ring elements, such that it satisfies two conditions. First, it satisfies these power sum relations between these k vectors and original vector f. And moreover, each of these k decomposed vector are having a much lower norms that goes from b to the k to b. And this can be instantiated by basically decompose every coefficient of every polynomial in its ring vectors. So given these two tools, there's a very natural way to do the folding without any norm blow-up. The idea is following. So the prover, given the instance with pair for these inputs, will first run this decomposition algorithm and decompose it to two k vectors of lower norms. It will compute the corresponding commitments and send these 2k commitments to the verifier. The verifier will then check that 2k commitments are consistent with the input commitments by checking this power sum relation in this commitment space. And after that, it suffices to prove knowledge of these 2k statements. And for that, we now use these low norm challenges, and the verifier will sample 2k challenges and do the randomly combination. And after the random combination, the resulting witness now will have a norm of approximately 2k times the norm blow-up lambda times b, which is the norm of each decomposed vector. So it turns out if k is large enough, this is actually even lower than b to the k, which is the norm of the input witness. So in sum, we obtain a scheme for which the output witness have an even lower norm than input witness. So we satisfy completeness without any norm blow-up. Unfortunately, this is not sound or knowledge sound. To enforce the knowledge soundness and prevent malicious prover, you really have to let the prover also provide a proof of knowledge that this decomposed vector are no norm. So lattice fold provides such a norm proof using the idea of sum check. Given these 2k statements that involves this matrix vector relation and norm statements, lattice fold represents 2k norm statements into a batch sum check instance. So what is sum check? Sum check is a claim for some multivariate polynomial of some degree that sum of the evaluation over the Boolean hypercube equals some claim values. And for that, we actually have a really classical protocol to check it in a very efficient way, for which the verifier is extremely efficient. And after that, and do the random combination, we can obtain a new statements that is basically just a new commitment opening relation with much larger norm bounds, plus a simple linear evaluation statement. And this actually serves as the actual accumulation scheme we have. That's also easier to fold. So first, this is good in terms of verifier complexity. However, the prover overhead is much larger, unfortunately. The reason is that given the input witness, which have a norm of b to the k, there are two options. The first option is to choose a large decomposition arity k, but that means you have to compute many commitments, which are these decomposed commitments. Another option is to make k smaller, but in this case, the b will be much higher, and sum check will have higher degree, and sum check prover will also be more expensive. The question is, can you achieve the best of both worlds? Can you have a low degree sum check and also make the number of decomposed commitments minimal? For that, we introduce a new range proof that directly works over this quotient ring RQ for some prime modulus Q. The key observation is that this RQ has a really rich algebraic structure that we can use to make the scheme much more efficient. To compare, in the lattice fold or ZQ setting, in order to represent these range D statements, you really have to translate it into algebraic formula of this form, okay, which has degree D. And this will translate to a degree D plus 1 sum check in the lattice fold compiler. So if D is large, that means the subtract will have high degree. That's the reason why you need to have decomposition. However, if you do this over RQ, you can do much better. So for the same statements, you only need to check a single ring multiplication. Essentially, you just check this value equals the constant term of a ring multiplication between a polynomial t and a monomial delta. Here, t is a globally fixed polynomial that embeds the range values into the coefficients of this polynomial. And if a is inside this range, then we can set delta to be x to the a, okay? And if you multiply this with t, then because x to the d is congruent to -1 this quotient ring, then the constant term will be exactly the coefficient of the degree x to the d minus a's term, which is exactly a. So this equation holds. On the other hand, if a is not in the range, no matter which monomial you choose, this equation will never hold. So this gives us both completeness and soundness. And even better, this is just a degree 1 equation between a fixed polynomial and some witness polynomial. So this idea leads to the following range proof. In order to prove knowledge of opening for the commitments, which is a ring vector of n, but also you can understand it as a coefficient matrix of integers with dimension d by n, and your goal is to prove that every entry is in the range of 0 to d minus 1. For that, the prover will send the commitments to these helper monomials, okay, which is large matrix, so you have to have some extra tricks to make it efficient to compute and also really small. And what we call it double commitments, which is inspired by the idea from Labrador, but we have some further improvements to enable folding for it. After that, it suffices to check these two relations I mentioned before. First is that every entry of f exactly equals the constant term of t times the entry of d. And second, you have to also make sure that every entry of d is indeed a monomial inside the set of 1x to x to the d minus 1. I'll omit the details, but it turns out we can represent this relation into a really succinct low degree sum check statements over ZQ, and that can be, we can run a really efficient sum check prover for it. And even better here, the prover only sends the single commitments rather than log D commitments in the last full setting, which leads to great efficiency. So this is the simple scheme, but the actual scheme is slightly more complicated. We have support more flexible normal ranges, smaller modulus Q for fast arithmetics, and also adapted techniques to fold committed R1CS relation, which is NP complete. So that's it. Basically, we built a new folding scheme from lattices, which is faster than Peterson-based hashes because we have faster commitments, but it's also more succinct and easier to construct compared to lattice-based succinct arguments because we are dealing with a weaker primitive. And the core technique to achieve this is a new lattice-based algebraic range proof that directly works over this RQ because it has really rich algebraic structure. I think I stop here, and the many interesting future work, for example, the currently proof analysis is this kind of classical random oracle analysis or interactive setting even, but we don't have a quantum random oracle analysis, which is ongoing work. Okay, so that's it. Thank you so much.
We have time for a quick question or two. I have one then. Can you tell us about the status of implementing the scheme and what was learned from it?
Oh, yeah, cool. So currently there's a company called Netherman. They have already implemented last fold, which is slightly weaker than this state-of-the-art elite curve setting scheme because of this the issue I mentioned that the prover needs to do more works. And they are actively implementing last fold plus. We hopefully like the scheme can be even faster than elite curve based schemes, but we have to wait until they finish it. Yeah.
Thank you.
Yeah.
Let's thank the speaker again then.
Thank you.
Forward, backwards.
Or backward.
Backwards from where you're.
Our next speaker is Roberto Parisella, who will speak about the knowledge soundness of Planck in Rome from falsifiable assumptions.
Yes, so thank you for the introduction. This is a joint work with Helger Lippma and Jan Osim. And oh, yeah. So the talk is divided into 3 parts. So I will mention some preliminaries. So I will try to explain what is Planck and why the previous security proof was not enough, why we needed a new one. And then I will explain our results, which are part 2 and part 3. But really, this paper is the last paper of an excitement research trilogy. So everything started in 2023, where in this TCC paper with Helger and Janno, we discovered that for some technicality, Planck proof does not translate into Planck security into the standard model. And then we start to deal with that. And we had a previous paper in the previous Eurocrypt. Here we developed a technique which helped us in following the issue. And particularly, we had a proof of security for a non-optimized version of Planck, and I will show later with a table why this was definitely not the end of the story. But hopefully, with this paper, now we have a proof of security, a realistic one, that Planck, as it is implemented, is secure in the random oracle model from falsifiable assumption. So let's start with the description of Planck. What is Planck? Well, I will describe it iteratively, starting from a very ideal version of Planck. First, let's think that someone publish a set of polynomials, like this indexer polynomial. And typically, this set of polynomial will define a class of languages. And then we have a very powerful ideal prover, like Alice here, which has the indexer and that statement and the witness. And we have Bob, the verifier, which has only the statement. This very powerful prover can send powerful messages. We can think of these messages as polynomials, so oracles that are real polynomials to the verifier. Then the verifier samples some challenges, for instance, a random field element. They go back and forth several rounds for this interaction. And then at the end, the verifier has several polynomial oracles. And the verifier uses this polynomial and the indexer polynomials to define this, like to evaluate a multivariate polynomial, getting in the end a huge univariate polynomial, and check if this polynomial that get in the end is the zero polynomial or not. If it is, okay, then this ideal verifier is convinced that the ideal prover knows the witness. We have the standard security properties, so completeness. Knowledge soundness means that here, if the verifier accepts, we can actually extract the witness from all the polynomials in the transcript. Zero knowledge, and then we have this succinctness requirement, which in Planck means that both the communication and verification complexity are independent of the size of the witness. And here, starting from an ideal protocol that is knowledge sound, it's quite an advantage because when we go to the real Planck, we actually only have to be sure that we extract the polynomial. And then we rely on this powerful knowledge extraction to compute the witness. Okay, so from this, we have to go to the real Planck. First, we weaken a bit the verifier. So now the verifier will not check a polynomial equation. Instead, we'll just sample a challenge, evaluate this huge univariate polynomial in this challenge, and check if this evaluates at 0. And with standard technique, this is more or less equivalent to the previous check, just a little bit more realistic. But in order to do a step forward, I have to introduce some notation, particularly the notation for cryptographic groups. So here in this paper, we use this bracket notation. So the group is additive. The group element is indicated with the X in bracket. So X is the order of the element. 1 in bracket is the generator. And we have our zoo of assumption, for instance, discrete logarithm, CDH, SDH, and many more. But actually, we require a little bit more structure, even though I will not go a lot into details on how we use it. We require bilinear pairing. So we have 3 of this group, G1, G2, and G target. All of them of the same order P, where P is a big prime. And then we require this pairing operation that will map the element of order X in group 1 paired with the element of order Y in group 2 into this element of order X times Y in the target group. This is basically a trick such that the verifier can perform one multiplication and check the result in this different group. And yes, okay, we also require no efficient isomorphism exists between group 1 and group 2. Okay, now that we have this structure, we can define this very powerful and nice primitive, which is called Kisei-G polynomial commitment scheme. The key generation is like here in the slide. We sample a secret trapdoor that is this field element sigma. And then we publish a bunch of group elements. So we have the group element in group 1 of order sigma to the various power up to n, where n will be the maximum degree of the polynomial we want to commit to. And then we have this 2 element in group 2, which will be used from the verifier, like these will be used at the verification procedure. What is important here is that the commitment is only 1 group element. So in order to commit to the polynomial f of x, we compute the group element of order f sigma, where sigma is in this secret trapdoor in the CRS. And we can do this efficiently just by group operation, taking the element in the commitment key. Then we have this opening procedure. I will not explain in the details. I will just say that the opening also is a group element. And we have this verification procedure, which will output 1 if and only if the verifier is convinced that f of alpha is equal to eta, where f is the secret committed polynomial, polynomial that is committed in C. Okay, so why this Kisei-G is so important? Well, one of the reasons is that there is this homomorphic property. So since commitment are group element, if we have commitment to f of x and commitment to g of x, we can homomorphically compute a commitment to a polynomial that is defined as a linear combination of f and g. And we will really exploit this property soon. Okay, so now we can move a step forward and check how it is, something that is closely to Plonk. So we had the Kisei-G commitment key in the CRS. And if we remember before, the ideal prover was sending polynomial oracles. Now the real prover will actually send a polynomial commitment. So particularly every time the ideal prover would have sent a polynomial oracles, the real prover just commits to it and send a commitment. They go back and forth with the verifier. So the verifier eventually has a bunch of commitment. Now the verifier sampled the evaluation challenge, but it cannot evaluate the polynomial by itself. That's not a big deal because the prover will evaluate for the verifier and will also provide the opening such that the evaluation will be done honestly. And then the verifier just check the correctness of the evaluation and check this evaluation of the big polynomial as the ideal verifier was doing before. Okay, but on top of that, we have 2 optimizations that we need to discuss in order to actually define the real fully optimized Plonk. The first one is called linearization trick, and is an optimization that takes advantage of the fact that the Plonk verification equation has that particular shape. So as you can see, like there are green polynomials that in verification equation appear inside the terms Sj, And then there is at most one purple polynomial that appears outside. So it is a sort of linear term of the verification equation. And we really exploit that in order to gain quite a lot in efficiency in the following way. So once the prover and the verifier have interacted, the verifier has commitment to both purple and green polynomial. The verifier sends the evaluation point. Now the prover only evaluates the green polynomials, but not the purple. And of course, compute the openings to prove that the evaluations are correct. Instead of evaluating the purple, the prover defined this polynomial hx in the slide, which, as you can see, is sort of linear in the purple. And then we'll compute an opening to prove that hx evaluated in the evaluation point is 0. And this is actually what the prover sent to the verifier. So now the verifier checked the correctness of only the green evaluations, homomorphically reconstructed the commitment to this polynomial hx by using a group operation, and then just check by this purple opening open h that this polynomial h evaluating in this evaluation point will give 0. So this is a very useful trick because we save a bunch of operations and we save a bunch of elements in the proof. And lastly, KZG has another layer of magic, which is it allows to batch openings all together. So as before, the prover compute all the evaluations of the green polynomial, and now just send the evaluation, but doesn't send the opening proof. Then it receives back another challenge. And finally, it can use this additional challenge to batch all the proof together in one single group element that acts as a batched opening proof. So now the verifier just compute the commitment to hx homomorphically and verify the correctness of all the openings in the protocol with one single opening, so with one single check. And this is actually how the full optimized Plonk look like. But why did I have to show all these details to you? Well, we will see very soon. So this can be summarized in a very popular framework to define snarks. We compile an information theoretic proof model and the KZG scheme into a succinct interactive argument. And then we apply the Fiat-Shamir transform to define a snark. What is the problem? Well, we need two ideal group models for the security of this framework. The first one is for the KZG security, where we need AGM or GGM. And then we need a random oracle model for the Fiat-Shamir transform. Also, how we use AGM and GGM in the KZG security, or how it was used in Plonk actually, it's problematic because it's a usage that does not translate into security in the standard model. Let's see why. So the KZG extractability in Plonk original proof is done in this way. We have a challenger that generates the commitment key, give the commitment key to the adversary compute a commitment. Well, if we are in AGM, there exists an extractor that just takes this commitment and output the committed polynomial. And this is crucial because this extraction only from the commitment without an opening is really used in the proof in order to prove that the linearization trick is sound, because in the protocol, we don't open the purple polynomial, as I showed you. But the point is that this kind of powerful extraction does not hold in the standard model, and we show an attack to this in 2023. So this is really the deal. We don't know if this attack translates to an attack to, we didn't know if this attack translates to an attack to the full Plonk or not. Okay, so we had this partial result last year in Eurocrypt when we showed that KZG is extractable actually under a falsifiable assumption in the standard model. And then we were able to show that a non-optimized version of Plonk is knowledge sound. But this was problematic because we don't allow for optimization, so no batching, no linearization trick, and we end up with a Plonk that was completely unusable. For instance, see here the difference in verifier complexity between our AC Plonk and the real Plonk. Moreover, there is another problem here. So when we use the Fiat-Shamir transform, we get a snark that is, if we start from a knowledge sound argument, we get a snark that has non-tight security. Particularly, we have a loss of q to the mu, whereas here q is the number of queries we can make to the random oracle. Mu is the number of round of the prover in Planck's protocol. Okay, but this loss is actually ignored in implementation because this would result in a Planck that is too much inefficient. Implementation assume that the loss is linear in Q, but this only holds if the interactive protocol has a stronger notion of soundness, like special soundness, as shown by Attema, Kramer, and Cole. So the real question is, in order to Planck to be secure as it is implemented, it has to be actually special sound, the interactive Planck. Is the interactive Planck special sound? Okay, so first we studied the soundness of the linearization trick. Recall the linearization trick take advantage of the fact that the verification equation has this shape, so we don't open the purple polynomial, instead we prove something about this polynomial hx. Okay, this is secure in AGM, of course. This is insecure in the plane model. There was another group, Fiore, Faoni, and Russo, that discovered the same attack basically in the same week. We were actually exchanging email and we were discovered that we were on the same page there. These groups also proved that the linearization trick is secure in a more realistic ideal model for group under standard condition on the purple polynomial, which luckily is satisfied by Planck verification equation. But we are interested in special soundness here. So our first result is actually a negative result. Under the discrete logarithm assumption, special soundness for the linearization trick is impossible in the standard model. And this can be extended to show that knowledge soundness is impossible in the standard model as well. And so this seems like it's the end of the story. Okay, if the linearization trick is not special sound, well, Planck used the linearization trick. Planck will never be special sound. And the proof in the Agimos is the best that we can hope, right? Luckily, we had a nice observation that linearization trick is a bit of an overkill for Planck because, okay, this is the verification equation of the linearization trick. The verification equation of Planck mostly has this shape that I show you on the slide. So some of the addends has this linear external part of polynomial. They don't use purple polynomial, or they don't use polynomial that are committed by an untrusted prover, but they use polynomial that are part of the index set. So they are committed in a trusted way, they are known by all parties, and particularly they are known by the extractor. And turn out, this is what saved Planck knowledge soundness, and this is what allow us to prove special soundness for Planck. So let me talk about the last part. We developed, or actually rediscovered, this technique. We give this nice name Reno, which stands for reduction to a hard assumption if not polynomial. This is the last technical challenge that we managed, so I will not go into the detail here. I will just say that this is the technique that allows us to extract the unopened purple polynomial in the case of Planck, when we have this particular case of the linearization trick. And particularly now we were able to show the full security for Planck. So using our Eurocrypt technique, we extract all the green polynomial. Here we had to prove that batching preserves special soundness, but that was not a big deal. Using this Reno technique, we also extracted the purple unopened polynomial. Then we proved that the underlying idealized protocol is also special sound. It has this stronger notion of soundness. So we extract a witness and we show that the full interactive Planck is special sound, which by Attema's et al. Result translate into the tightly knowledge sound of Planck in the random oracle model. And this is actually the end of the talk. So thanks for your attention. I just want to stress out that this was a really challenging task. This paper is only the last, but there were many people that worked such that now we have a nice and plausible security for this zero knowledge scheme. Thank you.
Questions to the speaker? Let me ask one then. There is an effort to come up with formally verified verifiers of Plonk by zkproof.org and others. Do you think that your proof is friendly to such formalization, or what can we hope for that would make it more friendly?
Well, so as far as I know, they want to formally verify a software implementation there, if I remember correctly.
Both.
Okay. I think, yes, our proof is actually very friendly with that, with the effort. And as far as I know, Plonk is now the only constant size snark that has this kind of nice proof of security, which only use falsifiable assumption and random oracle. I don't think it changed a lot in the effort of standardization and verification. I think it's like more a philosophical question. Like, okay, now we have really a plausible proof of security. Sorry. So it makes sense to standardize this scheme, because it would be very hard that someone would break a proof with this kind of reductions.
Thank you. I thank the speaker again.
Thanks. I see. Beautiful.
Our last speaker of the session is Bhaskar Roberts, who will speak about malicious security in collaborative ZK snarks.
Hi. So I'll start off with a definition. What are collaborative ZK snarks? They are multi-party computation protocols that compute ZK snark proofs. So in this setting, we have multiple provers. Each prover holds a fragment of the witness, and they'll engage in a multi-party computation that effectively combines all these witnesses together and generates one succinct proof that the witnesses are valid. This proof can be verified efficiently. Now, this protocol should have some notion of input privacy, meaning that each prover's input should not be leaked to the other provers. This is really a notion of zero knowledge, and the precise notion of privacy/zero knowledge that we need is called T0 knowledge, which was formalized by Ozdemir and Bonet in 2022. T0 knowledge says, let's allow the verifier to be corrupted, as well as up to T of the provers. And the witness fragments of the honest provers should not be revealed to the adversary. So T0 knowledge is the property that we will try to prove for our collaborative ZK snarks. And this turns out to be a surprisingly difficult task. Our first result actually presents some attacks which can break T0 knowledge if they're not handled properly. And prior work overlooked these attacks, so we believe it's important to highlight them here. Our second result is a positive one. We show that we can prove T0 knowledge against malicious adversaries. And in fact, malicious security comes for free. So what do I mean by this? Well, we typically start by designing protocols that are secure against semi-honest adversaries. These protocols tend to be simpler to reason about and more efficient. And then we can upgrade them to maliciously secure protocols using a generic compiler for malicious security. Now, our result says that this compiler is actually not necessary. The original semi-honest protocol was already maliciously secure. This is surprising and useful because it can lead to concrete efficiency gains. I'll mention there are a few caveats to our result. It only holds in the honest majority setting, and we have to assume the number of corrupted parties is exactly T. I won't get into the caveats too much, just know that they're there. So let's start with our first result, the attacks on T0 knowledge. The attack I'll present here exploits the fact that T0 knowledge is actually a stronger property than regular zero knowledge in the following subtle way. Zero knowledge only guarantees security when the witness is valid, whereas T0 knowledge must guarantee security for all witnesses, both valid and invalid. So zero knowledge says that if the witness is valid, then the proof can be simulated without any knowledge of the witness. T0 knowledge says the proof can be simulated for any witness, given just a single bit, indicating whether the witness is valid or not. So hypothetically, there could exist a proof system that satisfies zero knowledge, but if you run it on an invalid witness, the proof will completely leak the witness, hypothetically. Well, this is not hypothetical. In fact, Groth 16 is one such proof system. So how do we deal with this attack? Well, in the honest majority setting, there's a simple mitigation strategy. You have to verify the witness before generating the proof. And if the witness is invalid, don't output the proof. In the dishonest majority setting, even this mitigation strategy is not enough. There are some weird mauling attacks where the adversary can change their shares of the witness after it's been verified to change a valid witness into an invalid one. If you're curious about this, check out the discussion in our paper. Now let's move on to the second result, the positive result, which says that malicious security comes essentially for free. To understand what this means, let's revisit the typical design blueprint for collaborative ZK snarks. We start by designing a protocol that is secure against semi-honest adversaries, and then we upgrade it to a maliciously secure protocol using a generic compiler for malicious security. There's a long line of research on constructing these compilers, and many of them are based on the following idea of the additive attack paradigm. This basically says that a malicious adversary can only do one kind of attack, which is adding a known quantity to a multiplication gate. So let's take our semi-honest protocol and run it in the presence of a malicious adversary. Intuitively, we expect that the adversary can introduce errors and cause problems. The additive attack paradigm says there's only one kind of error, and it looks like this. If a multiplication gate was supposed to compute a times b, the malicious adversary can force it to compute a times b plus epsilon. Epsilon is a value that can be extracted from the adversary by the simulator, so it is in some sense known. And somewhat surprisingly, it turns out that any deviation the adversary makes from the protocol can be rephrased as an additive attack on some multiplication gate. It's also important to highlight that additive attacks do not break the privacy of the secret sharing scheme. So even if the adversary is introducing additive attacks, they can't learn any useful information from them until we reconstruct secret shared values. So armed with this tool, I can give some intuition for how most generic compilers for malicious security work. They simply work by detecting additive errors, and if they find errors, they abort the protocol before opening any secret shared values. And here's a list of some of the malicious security compilers in the literature. Now, this is a reasonable strategy, but it does require you to do some extra work to detect errors. Our approach is much simpler. We say, don't check for errors, just don't do it. This may strike you as dangerous or reckless, but rest assured that we have careful security proofs that back us up. One way to interpret this result is that the semi-honest versions of these protocols were already maliciously secure. So that's why we don't need to check for additive errors. But wait, this might seem weird. If the adversary is allowed to inject additive errors into the protocol, surely this must mess something up. Like for instance, they could force the output proof to be invalid. Yes, that's true. They could cause the proof to be invalid, but this isn't really a problem because the proof is designed to be verified. So the verifier will, in any case, detect if the proof has been tampered with. The key to our claim is proving that the additive errors don't allow the adversary to break T0 knowledge. Cool. So now I'll give some sense of how our security proof works. And rather than presenting the whole long collaborative zk-SNARK protocols, I'll do something simpler. I'll just present some subcircuits that appear frequently in these protocols, and I'll show how we argue security for these subcircuits. And this should give you a good impression of how our security proof works. The first subcircuit that appears frequently is a degree 2 function. This is a function whose multiplicative depth is 1. The key to analyzing this circuit is to realize that any errors introduced by the adversary are simply added on to the final output. So here is a circuit that's equivalent to the previous one. And in this circuit, the multiplication gates are computed without error. And it's only at the very end that the errors are added on to the output. Now, I'll give some intuition for why this circuit should still satisfy privacy. The output of this circuit with errors reveals the same amount of information to the adversary as the output of the circuit without errors. And this is easy to see because you can translate between the output with errors and the output without errors simply by subtracting the errors off. And the errors are known to the adversary and the simulator. So why do we care about degree 2 functions? These seem like really simple functions. Well, Groth16 is a degree 2 function. So the analysis that I've presented here will help us prove T0 knowledge for Groth16. Now, there's one subtle issue that arises when we're trying to prove T0 knowledge, which is the T0 knowledge simulator does not receive the output of some degree 2 function. It just receives a single bit indicating whether the witness is valid or not. So it's not immediately clear how we're supposed to simulate this whole degree 2 function with errors. And the basic idea is that Groth16 and these other proof systems already have a zero knowledge simulator designed for them. So we can use that zero knowledge simulator to compute the output of this circuit without any errors. And then at the end, we can extract the errors from the adversary and add them on to the proof. So here the ideal functionality is like the zero knowledge simulator, which outputs the proof without any errors. And all we need to do is add our errors on at the end. Here's the second subcircuit that appears frequently in our collaborative zk-SNARKs. This is a circuit that takes several uniformly random values as input. In this diagram, R and S are the uniformly random values as indicated by the blue circles. So how do we analyze this circuit? This is no longer a degree 2 function, so the analysis from before doesn't work. Here, the key insight is that the output of this circuit will be a uniformly random value due to the blinding random inputs. And notably, the output will still be uniformly random, even if the adversary introduces additive errors. So to simulate this circuit in the presence of errors, it's really simple. We just sample a uniformly random value, and this will be the correctly distributed output. So the previous two examples illustrate a new tool that we can add to our toolbox. Rather than trying to detect additive errors, let's simulate the output of the circuit even in the presence of errors. And this second tool is enough to allow us to prove malicious security for collaborative versions of bulletproofs and Groth16. For collaborative Plonk, our second tool is not quite enough. The reason is that collaborative Plonk is not actually maliciously secure automatically. So we will need to revisit this first tool and detect additive errors before opening the outputs. However, we're not going to use any generic compilers for malicious security. Instead, we have a much simpler way to detect additive errors. We simply verify the proof before reconstruction. Now, I want to highlight that we are verifying the proof inside of MPC before reconstructing plain text values of the proof. This is because if we don't do this, then if we reconstruct a proof that includes errors, this might leak information about the witness. So we verify the proof inside the MPC first, and then if verification passes, only then do we reconstruct the plain text value. So why is it that verifying the Plonk proof allows us to detect additive errors? Here's the intuition. Plonk is a delicate machine with lots of complex interlocking parts. And if the adversary introduces errors in this machine, it will mess things up completely and cause the output of the program to be uniformly random junk. In other words, if the adversary introduces errors, the output proof will be rejecting with overwhelming probability. So simply by verifying the proof, we can detect additive errors. We like this check because it's highly efficient. It requires only a constant amount of extra work. On the right-hand side, I've written out the final stage of our collaborative Plonk protocol. And in the green box is the check that we add to verify the proof. This check adds only a constant amount of extra work because Plonk was already designed to be efficiently verifiable. Finally, I'll conclude with some directions for future work. First, what other functions are out there for which the semi-honest version is already maliciously secure? It was surprising that collaborative ZK snarks have this property because they are non-trivial. And in light of this result, we expect that there are probably many other useful functions with this property. Our second question is, can this result be extended to the dishonest majority setting? So one of the caveats for our result that malicious security comes for free is that it only holds in the honest majority setting. This is because this is the setting in which the additive attack paradigm works the way that I said it does. In the dishonest majority setting, the attacks available to the adversary are much broader, and so it's not yet clear how to extend these ideas to the dishonest majority setting. And that's everything. Thanks for listening, and I'm happy to take any questions you may have.
Any questions to the speaker? This then concludes this session. Let's thank the speaker as well as the preceding ones again. We are off to a break.